Hi, everyone. Firstly, let me start by saying thank you very much for joining us today. As you can see, the topic of the webinar today is US terrain data sets, and we want to spend some time talking through FABDEM's work, building nationwide comprehensive, coherent terrain data sets in the US. A couple of housekeeping points before we get into it. Firstly, if you've got any questions, feel free to drop them in the chat. We'll definitely have time at the end to go through those. We'll also be doing a little poll at the end as well, so do keep an eye out towards the end of the presentation for that. Firstly, by way of introduction, if you don't know who I am, my name is Andy, a frequent member of these webinars, so hello again if you've been with us before. I'm one of the founders here at FABDEM, so I'm a flood scientist by background. I've spent my time in academia building computational flood models at large scales. I'm going to spend some time introducing terrain data sets themselves, giving you a bit of context around what these data sets look like, different forms of terrain data sets, and thinking about what they look like in the context of the United States. And then Hamish is going to join us, and Hamish really understands the detail of the work that's been undertaken because he himself has led a lot of our work processing and stitching together terrain data sets across the world. So Hamish will go into some more detail around how we've created this data set. Firstly, by way of introduction to FABDEM. So FABDEM was formed out of the University of Bristol in the UK. And the University of Bristol is one of the leading research groups in the world building computational flood models. And our aim actually was to build models of the whole planet. So as a research group, and indeed as an organization, our aim is to try and build these dynamic hydraulic models for the whole planet. And we are a research organization in many ways. We spend a whole bunch of our time publishing academic papers and engaging with academia. And we have quite a rich heritage of papers, actually going all the way back to the early 1990s. Now, you may be wondering what a flood modeling company is doing talking about terrain data sets. Well, actually, when you're thinking about building dynamic flood models, the most important component of those models is terrain data sets. Frankly, if you're simulating the dynamics of flooding and you're simulating how water flows, well, water flows downhill. And if you don't know where downhill is, then your model's not going to be very good. We have a history now of academic publications going back over the last 15 years, talking about how we can process terrain data sets to make them usable in flood modeling. And I would say that the flood modeling community as a whole is really one of the leading communities in the world, demonstrating how to get maximum usage out of terrain data sets. So I thought I'd start really simple, and that is by defining what a DEM is, a digital elevation model. Well, what is that? It's kind of in the name, I guess. It's a data set defining elevations. These typically take the form of grids, raster-based grids, defining elevations across the Earth's surface. And there's nothing new actually in these kinds of data sets. We have data sets that are incredibly precise and incredibly accurate in many areas. These data sets typically take the form of light detection and ranging data sets. And these are things we call LiDAR data sets. And again, at local scales, we can produce and build and have access to some really incredible terrain data sets. However, as I'll talk through in a moment, it becomes much more difficult at large scales. So firstly, thinking about local scale capabilities. Well, at really local scales, as I've mentioned, we can get access to incredibly precise and accurate terrain data sets. And I've chosen a model here of San Francisco Airport to illustrate this. And this is a storm surge model simulated over a 2-meter resolution LiDAR data set of the airport. And one of the things that we noticed when we were building these models is that the terrain data set was so precise that in fact it could pick up and detect even variations in the paint on the runway. So you could see the paint of the arrows on the runways. So we have incredibly precise terrain data sets available at local scales. And indeed, for the US, this is what LiDAR coverage looked like back in 2020 when we built the last version of our US flood model. And what you can see is that actually, for pretty extensive areas of the United States, we had these kinds of LiDAR data sets available for, again, quite large areas. The question then becomes, well, what do we do in the areas where we don't have LiDAR, in these white areas? And in these areas, they can be filled in with a multitude of different methods. And these can include things like satellite data sets, but also local scale point interpolation methods, kind of what I would call kind of more traditional, shall we say, methods of defining elevations. And with regards to some of the point elevation data sets, I've chosen an area here near the Ohio River to illustrate the differences that we see in flood models between the high quality LiDAR data sets and some of these legacy terrain data sets that have existed in the past. What you can see here is that where we have LiDAR, you can pick up some really amazing features in the floodplain. These lines you can see here are crevasse splays, so features created by different permutations and movements of the river and floods over time. But if you look down below, you can see some quite odd, obscure looking features. Now, these features are not real. These are, frankly, errors created by the methods employed to derive the terrain data sets in those locations. These are features that exist because of the point interpolation methods used to derive terrain data sets in these areas. And frankly, in these areas, kind of below that green circle, lots of the elevation data sets here are prone to a high amount of error. So what else can we do when it comes to trying to get a more comprehensive view of terrain and thinking actually on even broader scales for the whole planet? Like how do we get those data sets and what do they look like? Well, global terrain data sets do exist. We do have terrain data sets that give us views of the Earth's elevation for the whole planet. Now, the first versions of these were produced by the NASA shuttle going all the way back to the year 2000. And they derived using spaceborne radar. And at the time, they really were revolutionary. This is the first time we got global maps of the Earth's surface. And actually, I would say that collecting this data set with the shuttle, and what you can see here is that the shuttle actually had a radar boom that was flown out of the loading bay and flown around the world. The collection of that data set actually yielded our entire organization. Our field of building global scale flood models was made possible because of that data set being commissioned and put together. So it's a revolutionary data set. However, prone to very high levels of error. What you can see here, this is the Mekong Delta, and I've used this to illustrate some of the instrumentation errors with global terrain data sets as they existed a few years ago. Those lines are not real. They're actually caused by the pitch and roll of the spacecraft as it went around the planet. Another significant problem is that these global terrain data sets are not strictly terrain data sets. They're surface models. And that's because the radar signal bounces off the top of trees and it bounces off the top of buildings. So what you get is a map of the tops of trees and the tops of buildings. And for lots of applications, particularly flood modeling, what happens is that cities and towns begin to look like hills and they never actually flood, which is of course not true. So what we've undertaken is decades now of work figuring out how to process these kinds of terrain data sets. And if you keep an eye on the screen, I can show you what a cleaned up version of this terrain data set looked like. So this is an example of something called Merit DEM, and this is an example of where we got to with the shuttle radar topography mission data set. And this is what we built our global models off a few years ago. And again, the processing here is undertaken to remove artifacts, so buildings and trees. The great news is at global scales is that we now have a much better data set to work with, and that's been released by the European Space Agency. So last year, the European Space Agency released something called Copernicus DEM, and this is a terrain data set that's based off the TandemX mission. So this is a new spaceborne radar mission, which collected a radar surface model of the whole planet. And what we've done here at FABDEM, along with our partners at the University of Bristol, is to clean up that data set using all of the methods that I previously mentioned, so removing buildings and removing trees. We've actually used machine learning methods to do this, so new ways in which to process these kinds of terrain data sets. And the result is a true global terrain model at 30 meters for the whole planet. So the message here is that with this new global terrain data set, in lots of those gaps that we saw in the US, we can now fill these in with FABDEM, and this is what we're calling FABDEM, the Forest and Buildings Removed DEM. However, since 2020, it's not just the improvement of global scale terrain models that's happened. We've also collated and put together a significant improvement in the coverage of LiDAR. And again, if you keep an eye on your screen, this was the LiDAR coverage in 2020, and this is where we are now. So there's a significant amplification in the volume of LiDAR-based terrain data sets for the United States. And it's not just an improvement in coverage. Even in areas previously covered by LiDAR, we have new updated LiDAR as well. And you can see here that the kind of gray color is now covered by the FABDEM data set. These data sets have been collected from multiple sources, including from projects that we've undertaken with partners in the US. And to put some numbers to this, the LiDAR coverage has more than doubled, actually, just from 2020 alone. It's now 79% of the lower 48 states. And crucially, if you're an asset manager or somebody concerned with buildings, 94% of the buildings in the lower 48 states are now covered by LiDAR, up from just 58% in 2020. So we have a real significant improvement in the LiDAR inventory since 2020. And again, those gaps where we have no LiDAR are now filled in by the FABDEM data set. And this is what's comprising what we're calling the FABDEM plus data set. And in the United States, it has particular significance owing to the quite large volumes of LiDAR data that we have available. And it's not just the lower 48. If we look at the North America as a whole, you can see we have LiDAR and high-resolution terrain models available for large parts of Mexico and Alaska as well, and large parts of Canada. I'm going to wrap up my section with just by outlining some key features. Again, 94% of buildings in the lower 48 are now covered by LiDAR. We've collated here the best available terrain data sets, not just in the United States, but globally. We think we have the best comprehensive continuous terrain data set for the whole planet. The work here, which Hamish will go through in a moment, is really revolves around incorporating thousands of data sets in one place and stitching them all together. Crucially, when it comes to stitching together thousands of different data sets, we also include a metadata layer. So this is a way in which you can find out more about the data that underpins the terrain and the elevation that you're seeing in a location. So we give information on resolution, accuracy, the data source. The resolution here, where we have LiDAR data available in large parts of the US, we're providing this at around 10-meter resolution, so 1/3 of an arc second. And globally, it's 1 arc second, so around 30 meters for the whole planet. Again, this is the most up-to-date terrain data sets that we can get our hands on. And with regards to the global terrain models, these are now being independently validated by a peer review, and the FABDEM plus the FABDEM data set has been independently shown recently to be the best globally available terrain data set. Lastly, on access, I'll probably mention this at the end as well. We're trying to make these data as accessible as we can. They can be quite large. If you're thinking about grids that cover all of the United States or indeed all of the planet at high resolutions, they can be quite difficult to manage. That being said, we do provide them what we call on premises, so we can literally ship the data to you. But they're also available via FATHEM's API, so you can actually query as much or as little as you want via the API. You can send it points, you can send it polygons, and those can be as little or as much as you'd like. We also have a FATHEM portal now as well. So if you just want to visualize these data sets, you can do that via the FATHEM portal as well. So at this point, I will hand over to Hamish, and I will come back at the end just to talk through some use cases and some more on access. Do pop your questions in the Q&A box, and we'll get to them at the end. Hamish, over to you.
Yes, thank you, Andy. So yeah, I guess I'll be giving us a bit of an overview of the work that went into producing FABDEM Plus, particularly in kind of the USA and North America. So Andy's given you a pretty good idea, I feel, of exactly what FABDEM Plus is. A couple of more stats that I always think are good. In terms of population, we're covering 90% in the US and Canada. And since we're in the North American area, I thought I'd throw in that that's 45% of the population in Mexico as well. And I've already seen, to be fair, a question in the chat about what kind of data sets we are incorporating into this. So for the US, a few people asking about USGS, 3D and the 3D elevation program, and we are indeed sourcing a lot of our LiDAR data sets and high resolution data sets from these sources. So in Alaska, we are using INSAR, and in the US, it's mainly LiDAR, and a lot of that, again, comes from USGS, but not in its entirety. We also include sort of state-level data sets, which for well, a few different reasons haven't made it into the USGS collection. The 3D elevation program is a 1 meter data set that the USGS provides. And we did use the source data sets that come from, that feed into the 3D elevation program, but we didn't lift it directly from the 3D elevation program itself. And there's a couple of reasons that. One of them is when we started the 3D elevation program, didn't actually have it didn't have all of the data sets that were available in the original product resolution, and we wanted to get all of those. That's actually since been rectified, but there you go. That's the way things go, I guess. Another reason is not all data sets are included in that. And so to get a greater coverage, we also lifted some of the ones that weren't included in the 3D elevation program. So I think that kind of covers most of this slide, but I think before we move on, I'll also mention that while this is about the US, this particular webinar, this is, like Andy said, a global data set. So globally, we have over 12 million kilometers squared worth of either LiDAR high resolution data sets, and that covers globally over 900 million people. So, I mean, it's a lot, basically. It's sort of first of its kind as far as we in the team are aware. There's not really a globally consistent collection of LiDAR and high resolution terrain models available elsewhere, and there's certainly nothing that's been stitched into a first in class kind of underlying data set like FABDEM itself. Can I have the next slide, please? So jumping into the methodology then, and I'll try and keep this reasonably brief and high level to avoid boring anyone to death. But I think a big part of what makes FABDEM Plus so valuable is it's clean and it's consistent. There's a huge amount of processing that goes into producing global models. I mean, just the volume of raw LiDAR alone goes into the tens of terabytes. The processing time is, well, if we added it all up, it would probably be weeks, if not longer. And as part of this processing, we produce a consistent product at the end. So like Andy said, it's at either 1 or 1/3 arc seconds. It's all been reprojected to a consistent horizontal coordinate system, that being WGS84 or EPGS 4326, if you're more familiar with that. And another really key point is we've not just transformed it horizontally, we've also taken account different geoid and vertical data models used across the Earth. So before I kind of get into the details of that, I think this is a key point, because a lot of the time this is overlooked, even by GIS professionals. You download a data set, a DTM in this case, and you whack it on and you run your simulations on it, and you assume you're looking at, height above sea level or what have you. But depending on the geoid used, and indeed the underlying ellipsoid used, that can vary by, for geoids, it tends to be in the centimeters, but for ellipsoids, it can be in up to a couple of meters. So if you're using data sets which have not been transformed to the first vertical datum, you can have quite radically different pictures of the terrain surface. Now, these pictures might be fairly consistent, but they will be offset by that correction. So this is kind of illustrated in this diagram here that I pinched off this paper. And you can see the terrain in the brown, which is the orthometric height, or the terrain topographic surface. And that is defined by the height above the geoid. And the geoid is basically defined by the gravitational pull on the Earth's surface as any particular given point of the surface. And this is influenced by a whole variety of things, density of rocks and what have you. And this is generally sea level, as we would see it, where the sea would rise. So if you've got a minute after this, I would recommend looking up potato Earth. It generally gives you quite a nice picture of the Earth's geoid. But these vary country to country. They generally produce their own to get that little bit more accuracy. And then we have the ellipsoid as well. And again, these vary depending on country, again, to get that little bit more accuracy. So you basically end up with a range of different heights. You have the orthometric height, you have the geoid height, you have the ellipsoid height. And what we've done is we've made sure that you're always getting the orthometric height, and we're always using a consistent geoid. So you can be sure that wherever you are on the planet, that you're getting a globally clean and consistent measurement of height and terrain. And this includes across country borders. So you don't end up with jumps just because you're going into Canada, for example. Could I have the next slide, please? So then moving on from geoid corrections and regridding stuff, I'm going to spend a little bit of time talking about how we blended the data sets together. And this is actually, I was doing a little bit of reading on the 3D elevation program the other day. It is perhaps a point of difference between 3DEP and FABDEM Plus, is while they do say that all data sets are consistent within each data set, they actually don't guarantee that between data sets it's seamless. Now, I haven't actually had a really hard look with a microscope to see if there's any glaring issues, but we can say that all the blending across FABDEM Plus is consistent. So between data sets as well as within data sets, we're getting a nice smooth transition. And we do this in terms of just blending by a distance-weighted blending algorithm. So we use a pixel-wise method with a distance of approximately 300 meters. And that's approximately because since it's pixel-wise, the actual size of a pixel at 1 arc or 1/3 arc second varies depending on your distance from the equator. But it's roughly 300 meters of the equator. So where we have that full 300 meter overlap, if you see here on figure 1, if you imagine the little green double-sided arrows, the full overlap, we blend over this full 300 meters. And if you look at figure 2, we essentially, as we travel through, we take more from one data set than the other to produce like a weighted blend, which gives us a nice smooth transition, as you can see in this fabulous diagram that I made on paint. So what then really happens is when we don't have this full overlap, and I suspect this is why in the 3D elevation program they don't guarantee a clean blend always, is because if you don't have that distance, then it can be difficult to get a clean blend. So what we do to ensure that is we have a 3-tier algorithm that basically says if there's only a pixel overlap between these data sets, we'll take the average, because we still would generally consider that to be better than taking an underlying global product, where the resolution might be 30 meters, for example, and the LiDAR might be 2 meters. So we'll take the average, and then we move up to about half the distance of 300 meters. And if that's available, then we do the same weighted blend over that distance. And then finally, if possible, we take the full 300 meters. And this works across the whole data set. So this area where we have that 300 meter overlap, as you can see on figure 1, we'll have that full blend. And these areas shown in gray where we don't, we have the 1 meter, the 1 pixel blend, or the 150 meters, depending on what we have. So yeah, basically we always have the best possible blend depending on the level of overlap between the data sets. And as part of that blending process, we always ensure that the best quality data will be on top in any given area. So we ensure that by first checking data set type. If it's LiDAR, for example, it'll be above INSAR. Data set resolution, the higher the resolution, generally the higher fidelity of that product. And also the data collections. We ensure that the most recent and best data sets are always going to be shown to you when you buy the product. Next slide, please. So that's all the boring stuff. So let's look at some pretty pictures to do a little bit of qualitative validation. So on the left here, we have FABDEM, and on the right, we have FABDEM Plus, and this is somewhere on the Mississippi. And you can immediately see that in FABDEM Plus, we're getting a much more detailed appearing product, particularly around the Mississippi itself. We're removing quite a lot of noise. And over there, kind of on the left of the image, you can see we're picking up, rivers and meanders and stuff that are really not appearing particularly well in FABDEM itself. So LiDAR, is, as you would expect, at very low resolutions, 1-2 meters or below, is doing a better job than FABDEM, which is derived from satellites, 30 meters. Although again, I think it's key to point out that FABDEM is best in class. So even though there are errors here, they're much better than what else is available. Next slide, please. So taking a little bit of a trip into the past, if we compare FABDEM Plus now to NED, which is the National Elevation Dataset, I believe the precursor of the 3D elevation program, you can see we've had improvements here. And if you're wondering why there's big blackout bits here, I basically blacked out any areas where NED was using LiDAR data and just shown areas where they weren't. So you might look at these two images and your first thought is you can't actually see a huge amount of difference, but there are a few differences. So if we zoom in and we go to the next slide, this is an area near sort of the middle left of that image. And you can see with NED on the left here and FABDEM Plus on the right, the NED, even though they've done a good job, the USGS generally does a very good job on all the work they turn their hand to, but it is still unnaturally smooth. We're missing a reasonable amount of the detail of the actual landscape. And this kind of shows up in the little dots that you can see in FABDEM Plus, the greater granularity and the lack of aggressive smoothing, really, which has been added to NED. And if we go to the next slide, this is in a more urban area. And you can see that FABDEM Plus is picking up raised embankments and such for roads, a little bit more detail around kind of the fields around the middle of the image. And NED itself, while again, a good effort at data set, is again overly smooth and a little bit lacking in that detail. Next slide, please. And this is kind of a slide just to illustrate really the need for up-to-date LiDAR. Now, granted, LiDAR is always good. You'd rather have LiDAR from an earlier period, for example. Say LiDAR from 2013 would be preferable to a global DEM from 2015, just because of that higher resolution. But even relatively recent LiDARs, we have here 2017 to 2020, we've taken an anomaly map between two areas where there are LiDAR data sets. And you can see that there is quite a large change, up to 2 meters. It's the scales in meters, particularly in kind of riverine environments around deltas. We are seeing fairly large changes over those years. And we're also picking up mining works here as well. A lot of these larger kind of blocks of color in the middle of the image are where mining works have been undergone. And other construction work, for example, can change the face of the landscape. So up-to-date LiDAR basically is also good, rather than just resting on our laurels because we've got LiDAR in one place. Next slide, please. And the final little note for me really is talking about the metadata. So I actually saw there was a question about this as well while Andy was chatting about how do we define vertical accuracy. So vertical accuracy is actually a difficult one because in a lot of different data sets, it's recorded in different ways. So you might get standard error, mean absolute error, mean error, root mean squared error. But providing this is more difficult. But we do provide as part of that a certainty rank where we basically make an expert judgment here in FABDEM about how accurate a given data set is likely to be based on the urbanization of area, the slope of the area, forest cover, the forest height, and of course the underlying data type. So if the data type is good quality, it gets a good score. If the forest height is very high, then it's a bit more uncertain because algorithms have had to be used to remove this from the final products, and that's in LiDAR and other high resolution data sets. They still need to figure out what is ground and what is the canopy. Forest cover is similar, and urbanization as well, to be honest, because it's a canopy of buildings, if you like, rather than a canopy of trees, but the thinking is the same. And then slope we also consider, because generally in higher slope areas, you can imagine, for example, on a 30-meter data set, quite a lot of slope can happen within that pixel. So the height at one end is not the same as the height at the other. So that introduces uncertainty in itself depending on the steepness of the slope. So we provide that, which is something we're quite keen on. And if you follow FABDEM, our Chief Research Officer Ollie will be kind of introducing more of later on this year, I think. We also provide information in a geo package layer or a shapefile, if you're more familiar with that, of the source, where we got it from, the native resolution, what resolution it started at, the date, and the underlying data type, of course. And I believe that brings me to an end of my slides. So I'll pass back over to Andy.
Thanks, Hamish. And yeah, well done on your excellent diagrams conducted in paint. Very well explained. So just to wrap up, I thought it'd be useful to introduce what these products actually look like. So globally, in the worst case scenario for terrain modeling for the whole planet, and indeed in the US, the worst case scenario is that the data will be underpinned by FABDEM, which we've spoken about now at some length, but that's our global base layer effectively. The data themselves are available globally at 30-meter resolution. LiDAR exists in many areas in the US, in Europe. I think there's a question in the chat around Europe. We have LiDAR available in Japan as well, Australia. And as we've mentioned, the metadata to accompany this will also be provided. FABDEM plus 10 meters is possible, again, as we've mentioned, in areas like the US, in Europe, in Japan, in the UK. We can provide finer resolution terrain data sets as well. Just to spend a moment thinking about use cases and how you might actually deploy these terrain data sets. Now, the first thing that springs to my mind, being a modeler, is using these data sets to build improved hazard models. And indeed, you can do that. You can use these data sets for a whole range of different types of models, from flood models, wildfire, landslide models. You could use these data sets for logistical purposes, for disaster response. Planning as well is a hopefully quite obvious use case for these data sets. So think about site selection, exploring linear assets, and exploring perhaps exposure along linear assets, and indeed planning itself. So urban planning is an obvious use case. But even outside of those use cases, we're seeing these data sets now being used for things like digital twins. If you are, for example, to go and buy some real estate in Earth 2 in the metaverse, then the terrain you see in there is actually defined by FABDEM. It's defined by these global scale terrain data sets. And you can use these data sets even for things like gaming, sports applications. Really, anybody, and this is, I guess, in many ways an obvious statement, but anybody concerned with or who could make use of maps of the Earth's surface can get access to these terrain data sets and use and deploy them very quickly. I wanted to just say a quick word on a use case in which we've deployed these terrain models, and that is to build flood hazard models for all of Texas. So actually the Texan government have been fantastic in flying and procuring LiDAR data sets for the whole state. And we've used these new comprehensive LiDAR data sets to build flood maps for the whole state. So if you are in Texas, you can now get a LiDAR-based flood map wherever you are across the entire state, which, given the size of that territory, I think is quite extraordinary. In terms of access, I've kind of mentioned this already, but just to go through again, the API, the FABDEM API provides instant access to these data sets for as little or as much as you'd like. So you can send points, you can send areas, and you can get that data instantaneously. You can also view it via the FABDEM portal as well. So a nice GIS-based visualization platform for you to go and view and play around with the data sets can also be provided. We can also give these data sets directly. They can be provided with a simple AWS access ticket, and you can download these data sets, again, very quickly. And lastly, they do also exist via a number of our partners, and some of our partners are listed on the slide. If you are engaged with any third-party platforms in any way, let us know. It might be that we already have partnerships with them, and if not, they could be established. So we absolutely provide these data sets with partners as well. I think at this point, I think a poll is going to go live. So please do fill out the poll as it comes up on your screen. Hopefully it will. If you'd like to know more about data, book a demo. You can use the link there on the screen. We'll be at a bunch of up and coming events as well, both in the UK, in the US. So yeah, check that out. And if you'd like to come and see us in person, please do. We'd love to meet you. And yeah, please follow our channels as well. LinkedIn is probably the best place to follow us and keep up to date with everything that's going on here. With regards to the questions, I think Hamish has been doing a really good job actually at keeping up to speed with the questions as he's gone through the presentation. So good multitasking on his part. I think we've answered most of the questions. If I'm just looking through, I have a question on independent validation. Can we share the links? Absolutely. We will get the papers over to you. They're open as well, open access. So yeah, we can send you the links and you can read them. Does the data have improved resolution for Europe? The answer is it depends where in Europe. For lots of Europe, we do have LiDAR available, but not all of it. There are parts of Europe in which we don't have LiDAR, but for quite significant portions now of the continent, we do have LiDAR available. And we've actually used those to build a European-specific flood catastrophe model for the biggest insurance company in Europe as well. So we do have some really good data sets in Europe. And I think that actually brings us to the end, if there's no more questions. I will wrap up by saying thank you very much, everyone, for joining us. If there are any other questions you have, do feel free to drop us an email, get in touch. We'd love to hear from you. And as I've said, it would be great to meet you in person at one of our up-and-coming events as well. So again, thank you very much, and we hope to hear from you soon. Cheers.